When you're working with probability distributions, the expected value is just another name for the mean, which again is just another name for the average. So it's the average of what you think might happen. Now, it's got a couple of different notations. We write expected, E, value of X, X. Now, this is a capital X, notice, because it's the expected thing of what's going to happen, and that's capital X. We also can use the Greek letter mu. So get used to seeing either of these notations for your expected value. Now, think how you normally find mean. You add things together and then divide by how many there are. But if we're averaging outcomes from an experiment, then you have to consider how likely they are. Now, I'm going to start with a really simple experiment that we can work out without any prior knowledge, and then I'll take it into something new. So let's start by considering that I'm just rolling a normal six-sided die. These are the possible outcomes, all the numbers 1 to 6, and they're all equally likely. There's a chance of 1 out of 6 of it landing on any one of those numbers. So if I'm thinking about what the expected value is, or the average outcome, it makes sense that if I add them all together, 1 plus 2 plus 3, that's 6, plus 4 is 10, 15, I get 21. And if I find that I do 21 divided by 6, because that's how many things there are, this is a really okay way to do this example. And the reason it's going to work is because all of the outcomes are equally likely, so I don't have to be too careful. Now, what is 21 divided by 6? Well, it's 3.5. Now, let's think about what that really means. It means that the average number that I'm going to get when I toss a die is 3.5. Now, I can't actually roll 3.5. But 3.5 is the average of all of these numbers. So I've written here, this makes more sense, finding the expected value of an experiment like this, if you're considering doing the experiment lots of times. For example, it's impossible that you'll get 3.5 when you roll a die, but if you were going to have someone, say, roll the die 100 times and add up their score every time, and you had to bet on what their total score might be at the end of 100 rolls, it would be really useful to know that the average roll is going to give you around about 3.5. So multiplying that by 100 and saying they're probably going to get somewhere around about 350 would be a pretty good guess. Now, that doesn't mean they'll get 350, but it gives you some ballpark idea of what might happen. It tells you what you are expecting. Now, what if this die was weighted so that all of the outcomes weren't equally likely? Can you see how if it was more likely to land on a 6, that would make the expected value go up, wouldn't it? So we're going to have to consider a different method. Now, we worked out that expected value when we roll the die of 3.5, just by using sheer logic, assuming that the probabilities wouldn't matter because they're all the same. We just added the outcomes up and divided by how many there were, and we got 3.5. But let's have a look at how else we could have done it, so that if we do have probabilities that are not all the same, we'll have ourselves a method. Well, didn't we add all of the outcomes together and divide by how many there were? Sure, that's another way of setting it out. And isn't that the same thing as breaking this fraction up so that we've got 1/6 plus 2/6 plus 3/6 right up to 6/6? That too gives 3.5, doesn't it? Yep. And isn't that exactly the same as saying we've got 1 times a 6th plus 2 lots of a 6th plus 3 lots of a 6th, etc., right up to here. Now, why have I broken this up? I'm not trying to make more work for myself, but this is another way of understanding what it was that I actually did. And here I've broken it up so that I can see my probabilities popping up in my working. Now, it seems that what I have to do is multiply each outcome by its probability and then add them together. And that gets me my 3.5. So, let's look at another way that we could set this out so that we've got a method for when things get a little bit more tricky. We need to multiply each outcome by its probability. So let's call this line x multiplied by p of x. You can put a dot between the x and the p if you like. I prefer to do that just to show it's two separate parts and it reminds me what to do. Now we've got 1 times the 6th, 2 times the 6th, 3 times the 6th, and obviously we know the answer to this, but I'm just practicing my setting out here because this is a process that you won't have necessarily done before. Now, On this table, I've got everything I need. I just now need to add up all of the numbers that have been multiplied by their probabilities. So the sum here, I'm just going to get rid of that. I should have done it further over. Let's put a sum column. Now I know that if I add all the probabilities together, I should get 1. So it's kind of handy having a sum column there so I can just check that these are actually right and they do add up to 1. But here, once I find the sum of these, which is going to be 21/6, which I could also just write as 3.5. When I set my table out this way, this is going to be my expected value, or mu. And now I've got a method for finding it when the probabilities actually aren't all the same. So how would we put that as a formula? Well, we'd say the expected value of x is equal to the sum of, remember we've seen that notation before, take the sum of each outcome multiplied by its probability, x, px. And that is the formula for expected value when you're dealing with probability distributions. Okay, so let's use this formula that we've just found to investigate a different experiment. In this experiment, I'm rolling a die again, but this die is not a normal one. I've actually been a bit sneaky and I've put a weight on the side of the die that's got the number 6. So the probability of getting a 6 is 0.3. The probability of all of these numbers, which are probably around the sides from the 6, are all the same, 0.15. And the probability of getting a 1, well, that number's opposite the 6, so it's the least likely thing that's going to happen if I've got weight on that side. Still might happen depending on how it bounces, 0.1. Now, you'll notice that all of these probabilities add up to 1. This is almost like just a little check to make sure that anything you've put in here is actually going to work and that this experiment is a legitimate situation. Now I've got my method, I need to add up all of the numbers multiplied by their probabilities. Now, what are you expecting the expected value to be? For the unweighted die, it was 3.5, wasn't it? So if we've made it much more likely to land on the 6, we've probably made the expected value a bit more than 3.5. And that's worth thinking through so that our answer makes some sense. All right, 1 multiplied by 0.1, I can do that in my head. 2 lots of 0.15, that's 0.3. Now you can use a calculator for any of these if you like. 3 times 0.15, that's 0.45. 4 lots of 0.15 is 0.6. 5 lots of it is 0.75. You'll notice it's going up by 0.15 at a time. And 6 lots of 0.3 is 1.8. So then adding these together, I get 0.4, 0.85, 1.45, 2.2, I get 4. Now you could use your calculator obviously to add those up, make sure that you don't make a mistake. And I've quite quickly and easily found that the expected value when I roll this die is a 4. Now 4 in this case is an actual possible outcome, but it might not have been. And certainly this expected value doesn't have to be an outcome that could happen. It's the average of the outcomes.